The SN1 reaction from a stereochemical point of view. We have a secondary alkyl halide here. Notice that the alpha carbon is attached to 2 carbons, so it's a secondary alkyl halide. And we're going to do the SN1, and we know that because a secondary plus a weak nucleophile has to undergo the SN1 reaction. The nucleophile has to be strong to do an SN2. But in the first step of the reaction, the iodide is going to leave, and it leaves behind a nice stable carbocation. This one is a secondary carbocation. Now, in terms of geometry, the carbon of the carbocation is an sp2 carbon, and sp2 carbons are trigonal planar. That's very important because if it's trigonal planar, that means that that carbocation that I have right here is flat, and right now it's lying on the plane of the paper that I have here. So there's the p orbital is coming out of the paper, and the back lobe is behind the paper. So what's going to happen right here when the water attacks? Well, if the water attacks from the front, we will end up with the OH in the front, but the water could attack the carbocation from the back, and that way the OH will be in the back. So let's assign the R and the S to our new alcohols right here. Alpha carbon has an oxygen, a carbon, and another carbon, so oxygen is 1. The ethyl is 2. And the methyl is 3. So this carbon right here is the R, is clockwise. So this is the R enantiomer. And this is the opposite. So this one has a hydrogen pointing to the front. So it's R, but hydrogen is in the front. So it's S. So when you do an SN1 reaction, because your carbocation is trigonal planar, you're going to end up with a mixture of enantiomers right here. So you get what they call inversion of configuration, but you also get retention of configuration. So you get a mixture of inversion and retention of configuration. And that is the stereochemical perspective of an SN1 reaction.